Okay, so last time we kind of got our feet wet with that survey paper
Yeah.
on attention heads in large language models.
Right.
This time,
Fascinating overview.
yeah,
Setting the stage.
yeah. And this time we're diving headfirst into the technical depths.
Where the magic truly unfolds.
I love it. Okay, so for all you PhD students out there, get ready for a deep dive into the mathematical foundation of attention mechanisms.
Mm-hmm.
Think of it like learning the secret language of LLMs.
The code that makes these models tick.
Precisely. And the paper starts by breaking down these incredibly complex systems, LLMs, into digestible pieces,
Right.
starting with the fundamental mathematical representation.
Think of it like a blueprint,
Okay.
guiding us through the LLM's architecture.
I love it. So they use the decoder-only LLM structure as our model.
Exactly.
Right.
And the decoder-only structure simplifies things a bit for us,
Right.
allowing us to focus on the core components without getting bogged down by the encoder part.
Okay, so decoder-only it is.
Yeah.
Let's take this guided tour of the LLM's anatomy.
Sure.
Starting with the embedding layer.
Okay.
What exactly happens there?
Well, the embedding layer is where the magic of transforming words into numbers happens.
Okay.
Think of it like this. Each word in our vocabulary is assigned a unique vector,
Right.
a set of numbers that captures its meaning
Okay.
and relationship to other words.
It's like giving each word a personality profile, right?
Mhm.
A numerical fingerprint that tells us what it's all about.
That's a great way to put it.
Yeah.
These numerical representations or embeddings
Right.
allow the LLM to understand words not just as isolated units, but as parts of a complex web of meaning.
Fascinating.
Yeah.
So once we have these numerical representations, where do they go?
The heart of the LLM, the decoder blocks.
What's the next stop on our LLM tour?
These blocks are the workhorses of the system,
Okay.
processing and refining the information from the embedding layer.
I'm picturing these blocks as mini factories,
Yeah.
each one performing a specific task to transform the raw material, the embeddings, into a finished product. The LLM's output.
A very apt analogy.
I try.
These decoder blocks are stacked on top of each other,
Okay.
and the output of one block becomes the input for the next.
Right.
It's like an assembly line where each stage adds a layer of sophistication to the processing.
And how many of these decoder blocks are we talking about? Do all LLMs have the same number?
The number of decoder blocks can vary
Sure.
depending on the size and complexity of the model.
Right.
Some models might have just a handful,
Right.
while others can have dozens or even hundreds.
Wow.
The more blocks you have, the more processing power the LLM has, allowing it to handle more complex tasks and understand nuanced relationships between words.
It's like adding more layers to a cake.
Precisely.
Each layer adding to the overall richness and complexity of the flavor.
And within each of these decoder blocks lies the real star of the show, the attention mechanism.
Okay, I've been waiting for... This attention has been hyped up so much.
Yeah.
It's almost mythical.
Yeah.
Can you demystify it for us?
Sure.
What exactly is the attention mechanism?
At its core, the attention mechanism allows the LLM to focus on specific parts of the input that are most relevant to the task at hand.
So it's like a spotlight shining on the important parts while dimming the rest.
Exactly. Imagine you're reading a long text and your mind naturally focuses on certain words or phrases that stand out as important.
Like the key words that help us understand the main points of the text.
That's precisely what the attention mechanism does.
Okay.
It does so in a much more sophisticated and nuanced way.
Okay, and how does it actually work? How does the LLM decide what to focus on? Is it some sort of AI intuition?
Not quite intuition, but rather a brilliant mathematical algorithm.
Okay, I'm intrigued. Break it down for us.
Okay.
What are the key elements of this attention algorithm?
The core of the attention mechanism lies in the interplay between three key elements: queries, keys, and values.
Queries, keys, and values. It sounds like we're on a treasure hunt.
Think of it this way. Imagine you have a question in mind, a query, you're looking for information, and you need to search through a vast library of data. This library has keys associated with the different pieces of information, like labels on bookshelves.
Right.
And the actual information you're looking for, the content of the books, are the values.
Okay, so the LLM takes the input text, breaks it down into words or tokens, and transforms each of these into a query, a key, and a value.
That's exactly right. Each word or token is represented by these three vectors, each playing a specific role in the attention mechanism.
Got it. So the query is like the question the LLM is asking. The key is like a label that helps find the relevant information, and the value is the information itself.
Precisely. Now, the real magic happens when we calculate the similarity between each query and every key in the input.
What?
The more similar a query is to a key, the more relevant that piece of information is considered to be.
So it's like a matching game, finding the best fit between what the LLM is looking for and what's available in the input.
Exactly. And this is where the math gets really interesting.
Okay, hit us with the math. I'm ready.
The heart of this calculation lies in the scaled dot product attention mechanism. Essentially, we're calculating the dot product between each query vector and every key vector in the input.
Dot product. That takes me back to linear algebra. Can you refresh our memory on what that means?
It's a way to measure the similarity between two vectors.
Okay.
Think of each word as emitting a signal, and the strength of that signal depends on how closely related the words are.
Okay.
The dot product is like a receiver picking up on those signals and amplifying the ones that are most relevant to the current query.
Okay, that makes sense. So the higher the dot product between a query and a key, the stronger the signal, the more relevant that piece of information is.
Precisely. And once we have these similarity scores for each query key pair,
Right.
we normalize them using a softmax function.
Right.
This creates a probability distribution, assigning a weight to each value based on its relevance to the query.
So we're not just saying this is relevant, that's not. We're actually giving each piece of information a score,
Exactly.
a probability indicating how strongly it relates to the query.
These probabilities then determine how much each value contributes to the final output of the attention mechanism.
Okay.
You can think of it like a weighted average,
Right.
giving more weight to the information that's most relevant to the query.
So the LLM is essentially creating a custom-tailored summary of the input,
Precisely.
highlighting the key points based on the query.
It's like a super-powered version of our own attention,
Yeah.
allowing the LLM to sift through vast amounts of data and focus on what's truly important.
This is amazing. It's like we're giving the LLM a superpower,
Right.
allowing it to understand and reason with language in a way that was never possible before.
It truly is a game
But
changer.
we're not done yet, right? The paper mentions something called multi-headed attention. What's that all about?
That's where things get even more interesting. Imagine, instead of having just one spotlight, we now have multiple spotlights, each shining on different aspects of the input.
Multiple
Yeah.
spotlights. So instead of just one perspective on the information, we're getting multiple perspectives, each highlighting different aspects of the text.
That's the idea. In multi-headed attention, we have several attention mechanisms working in parallel, each with its own set of queries, keys, and values.
Wait, so each head has its own unique perspective on the input. That's incredible.
Exactly. This allows the LLM to capture different types of relationships between words and phrases.
Okay.
For example, one head might focus on the grammatical structure of the sentence, another on the semantic relationships between words, and another on the overall context of the text.
So it's like having a team of experts,
Yes.
each analyzing the text from their own specialized perspective,
Yeah.
and then combining their insights to create a more nuanced understanding.
A perfect analogy, and the beauty of multi-headed attention is that it allows the LLM to learn these different perspectives automatically during training without us having to explicitly program them in.
Wow, this is mind-blowing. It's like we're giving the LLM the ability to develop its own intuition about language.
It's a fascinating area of research.
Yeah.
And we're only just beginning to understand the full potential of multi-headed attention.
This deep dive has already been an eye-opener. I'm starting to see LLMs in a whole new light, not just as tools,
Right.
but as complex systems with their own unique way of thinking.
It's a journey of discovery, and we're just getting started.
I can't wait to see where this journey takes us. But before we get lost in the excitement, I think we need a little break to process all this amazing information.
A wise suggestion. Let's take a moment to let it all sink in.
We'll be back soon to continue our exploration of multi-headed attention and its impact on the remarkable capabilities of LLMs. Okay, so we've laid the groundwork, exploring those decoder blocks and the fascinating world of attention mechanisms. I'm ready to dive deeper into this multi-headed attention concept.
An excellent choice. Multi-headed attention is truly at the heart of what makes these LLMs so powerful.
I'm all ears.
Oh.
Let's unravel this multi-headed mystery. Remind me again, why is it called multi-headed attention? What's so special about having multiple heads?
It's all about perspective, or rather multiple perspectives. Instead of relying on a single attention mechanism to process information, we have several of these mechanisms, each with its own set of queries, keys, and values working in parallel. Each head can focus on a different aspect of the input, like a team of experts analyzing a problem from different angles.
Okay, I'm starting to get the picture. It's like having a linguist, a grammarian, and a logician all working together to understand a sentence.
Precisely. Each head brings its own unique expertise to the table, allowing the LLM to capture a richer, more nuanced understanding of the text.
So we've got these multiple heads, each with its own set of queries, keys, and values. But how do they actually work together? Do they just operate independently and then combine their results at the end?
It's a bit more intricate than that. Each head performs the same basic attention operation we discussed earlier, calculating similarities between queries and keys, generating weights, and producing a weighted sum of the values. But here's the key. The outputs from all the heads are then concatenated or combined together.
So it's like taking the reports from each of our experts and merging them into a single comprehensive document.
Exactly. And this concatenated output is then passed through a linear transformation, a mathematical operation that helps to integrate the information from all the heads and create a unified representation.
Okay, so we're not just adding the outputs together, we're applying another layer of processing to blend them seamlessly. But why go through all this trouble? What are the benefits of having these multiple heads working together?
There are several key advantages. First, it allows the LLM to capture different types of relationships between words. One head might focus on syntactic dependencies, identifying subject-verb relationships, while another head might focus on semantic similarities, recognizing synonyms or related concepts.
So it's like having different lenses, each revealing a different facet of the language.
That's a great analogy. And by combining these multiple perspectives, the LLM can build a much richer and more complete understanding of the text.
Okay, that makes sense. What other benefits does multi-headed attention bring to the table?
Another key advantage is robustness. If one head happens to miss an important piece of information, other heads can compensate for it. This parallel processing approach makes the LLM more resilient to noise or errors in the input.
It's like having a safety net, ensuring that the LLM doesn't trip over a single missed detail. What about efficiency? Does having multiple heads slow down the processing?
Surprisingly, no. Modern hardware is optimized for parallel computation, and multi-headed attention can actually speed up the training process. Instead of processing the information sequentially, we can divide the workload among multiple heads, each working concurrently.
So it's like having a team of workers instead of just one, allowing us to complete the task much faster.
Exactly. And this parallel processing capability becomes even more crucial as we deal with longer and more complex texts. Multi-headed attention helps to distribute the computational load, making it possible for LLMs to handle those massive data sets that are now commonplace in AI research.
This multi-headed attention concept is brilliant. It's like we've taken the basic building block of attention and amplified its power by orders of magnitude.
It's one of the key innovations that has fueled the remarkable progress we've seen in natural language processing over the past few years.
So if I understand correctly, multi-headed attention allows the LLM to process information more effectively, capture different types of relationships, and handle larger data sets. But how does this translate into real-world capabilities? How does it impact the tasks that LLMs can perform?
The impact is profound. Multi-headed attention has been instrumental in advancing a wide range of NLP tasks, from machine translation to text summarization, from question answering to chatbot development.
Give us some specific examples. How has multi-headed attention revolutionized these areas?
Take machine translation, for instance. Before, multi-headed attention models struggled to capture the nuanced relationships between words in different languages. But with multi-headed attention, they can now attend to different aspects of the source sentence, such as word order, grammatical structure, and semantic meaning, and use this information to produce more accurate and fluent translations.
It's like having a translator who can not only understand the words, but also the subtle nuances of grammar and meaning.
Exactly. And in text summarization, multi-headed attention allows the LLM to identify the most important sentences in a document, even when those sentences are scattered throughout the text. It can attend to both the local context of each sentence and the global structure of the document, creating a more comprehensive and informative summary.
So it's like having a speed reader who can instantly grasp the key points of a lengthy article.
Precisely. And in question answering, multi-headed attention helps the LLM to identify the relevant information in a passage and use it to answer the query accurately. It can attend to both the question and the context, ensuring that the answer is both relevant and correct.
It's like having a research assistant who can quickly find the needle in the haystack of information.
A very apt analogy. And these are just a few examples. Multi-headed attention is now a standard component of most state-of-the-art NLP models, and its impact is being felt across a wide range of applications.
This is truly remarkable. It's like we've unlocked a new level of language understanding, and the possibilities seem endless.
It's an exciting time to be working in this field, and the pace of innovation is only accelerating.
I'm eager to see what the future holds. But before we get too far ahead of ourselves, I think we need to take a step back and appreciate the complexity of what we've just explored.
Indeed, multi-headed attention is a sophisticated mechanism, and it's taken years of research and development to reach this level of understanding.
I'm starting to feel a bit overwhelmed by all the technical details.
hmm
Is there a way to simplify this concept to get a more intuitive grasp of how it all works?
Of course, sometimes stepping away from the mathematical equations and using analogies can be helpful. Think of each head as a different filter, each designed to extract a specific type of information from the input. One filter might highlight the grammatical structure, another the emotional tone, and another the logical relationships between concepts.
So it's like having a set of colored glasses, each one revealing a different layer of meaning in the text.
Precisely. And by combining the outputs from all these filters, we get a more complete and multifaceted representation of the information.
That's a much easier way to visualize it. It's like taking a black and white photo and suddenly seeing it in full color.
And just like with colored glasses, each head can emphasize certain aspects of the information while downplaying others. This allows the LLM to focus on the most relevant details for the task at hand.
Okay, I think I'm starting to get a handle on this multi-headed attention thing.
Hmm.
But I have a feeling there's still more to learn, right? Where do we go from here? What other mysteries lie hidden within these attention mechanisms?
There's always more to uncover. In our next deep dive, we'll explore how these attention heads specialize even further, becoming experts in specific cognitive tasks, like knowledge recall, logical reasoning, or even sentiment analysis. Get ready for a fascinating journey into the inner workings of these special attention heads.
Okay, so we've uncovered the power of multi-headed attention, but I'm still curious about the nitty-gritty details. How do we actually implement this concept mathematically? What equations are we talking about?
It's all about matrix operations, which computers excel at. Imagine we represent our queries, keys, and values as matrices, essentially tables of numbers. Each row in the query matrix corresponds to a query vector, each row in the key matrix to a key vector, and each row in the value matrix to a value vector.
Okay, so we're organizing all those vectors into these neat little tables. What happens next?
We perform a series of matrix multiplications. First, we multiply the query matrix by the transpose of the key matrix. This gives us a matrix of attention scores, where each entry represents the similarity between a query and a key.
Transpose. That rings a bell. Can you remind me what that means?
Essentially, we're flipping the key matrix along its diagonal. Rows become columns, and columns become rows. This allows us to align the dimensions of the query and key matrices for multiplication.
Got it. So we multiply the query matrix by this flipped key matrix, and that gives us a matrix of similarity scores. What do we do with those scores?
We scale them down by a factor related to the dimension of the key vectors. This helps to stabilize the training process, preventing the scores from getting too large. Then we apply the softmax function to these scaled scores, converting them into probabilities.
Right. The softmax function, it turns those raw scores into something more meaningful. A probability distribution that tells us how much attention to pay to each value.
Precisely, and finally, we multiply this probability matrix by the value matrix. This weighted sum of the values gives us the output of the attention mechanism.
So it's like taking a weighted average of the values where the weights are determined by the attention scores.
That's a great way to put it. And remember, in multi-headed attention, we repeat this process for each head. Each head has its own set of weight matrices, allowing it to learn different attention patterns.
Okay, I think I'm starting to see the mathematical beauty of it all. It's amazing how these simple matrix operations can capture such complex relationships between words.
It's a testament to the power of linear algebra and its ability to represent complex transformations in a concise and elegant way.
I'm ready for a challenge. Can you walk me through an example, maybe a simple sentence, and show me how these matrices would work together?
Absolutely. Let's take the sentence. The cat sat on the mat. We'll need to first convert each word into a vector representation and embedding. Let's assume for simplicity we're using four-dimensional embeddings. So the might be represented by a vector like zero point 0.2, zero point 0.5, zero point 0.1, 0.8, capped by 0.6, 0.3, 0.7, 0.2, and so on.
Okay, so we have our word embeddings. How do we form our query, key, and value matrices?
We could have separate matrices for queries, keys, and values, but for self-attention, a more common approach is to use the same input embeddings to generate all three. We apply three separate linear transformations, each represented by a weight matrix, to the embedding matrix. One transformation produces the query matrix, another the key matrix, and the third the value matrix.
So we're multiplying our embedding matrix by three different weight matrices to get our queries, keys, and values. Why do we need separate weight matrices?
Think of it this way. Each weight matrix is like a lens that focuses on a different aspect of the word's meaning. The weight matrix for queries might emphasize the word's role in asking a question, while the weight matrix for keys might highlight its role as a label or category.
I see. So we're essentially transforming the embeddings into different representations depending on whether we're using them as queries, keys, or values.
Precisely. And these transformations allow the model to learn how to best use each word in the context of attention.
Okay, so we have our query key and value matrices all derived from the original word embeddings. What happens next?
Now we can perform our matrix multiplications. We multiply the query matrix by the transpose of the key matrix scale. The results apply the softmax function and finally multiply by the value matrix. This gives us the output of the attention mechanism for a single head.
And in multi-headed attention, we would repeat this process for each head, right? Each head would have its own set of weight matrices resulting in different attention patterns and outputs.
Exactly. And those outputs would then be concatenated and passed through another linear transformation to create a unified representation.
Wow, it's amazing to see how all these pieces fit together. But I have to admit, it's still a lot to wrap my head around. Is there a way to visualize this process to make it more concrete?
Absolutely. Many visualization tools can help us understand how attention works. These tools allow us to see which words or phrases the model is focusing on for a given input. We can see how the attention weights change as the model processes the text, revealing the underlying reasoning process.
So it's like peering into the LLM's mind and seeing how it connects the dots between words and concepts.
Precisely. And these visualizations are not only fascinating from a research perspective, but they can also be incredibly useful for debugging and improving our models.
I can imagine if we can see where the model's going wrong, we can adjust the training process or even tweak the architecture to improve its performance.
Exactly. Visualization tools are becoming increasingly important as we strive to understand and control these powerful LLMs.
This deep dive has been an incredible journey. We've gone from the high-level concepts of attention to the nitty-gritty details of matrix operations and visualizations. I feel like I've gained a much deeper understanding of how these remarkable models work.
It's been a pleasure exploring the world of attention with you. And remember, this is just the beginning. There's so much more to discover, so many exciting avenues for research.
I can't wait to see what the future holds. But for now, I think we've earned a break. Thanks for joining us on this deep dive into the fascinating world of multi-headed attention. In our next episode, we'll be exploring how these attention heads develop specialized skills, becoming experts in specific cognitive tasks. Get ready to meet the special attention heads. See you then, Munchley.